Jabalisco here with a little explanation of a topic covered in my book, Teach Yourself Electricity and Electronics. All editions cover this topic. I'm looking at the 5th edition right now. That's edition number 5, in which transformers and impedance matching are discussed in chapter 18, which begins on page 304. And I have created here a generic diagram of a transformer with a powdered iron core. You can tell it's a powdered iron core because of these two dashed lines between the turns. Dashed lines means a powdered iron core. If they were solid lines, they would be laminated iron. If there were no lines at all, it would be an air core coil. A powdered iron core is commonly used in an audio frequency or AF transformer for the purpose of matching impedances. Well, I suppose they're not used as often these days now that everything can be put onto a single integrated circuit chip. An entire stereo radio can be put onto an integrated circuit chip, and transformers have largely been done away with, except in high power applications like you would find with extreme production systems in auditoriums and in certain high fidelity recording systems. Some music bands still prefer this older technology, and they can be used. You can always use a transformer to match impedances if you need just a specific device to match impedances. The thing that you need to keep in mind whenever you use any kind of impedance matching transformer like this is that you can't have any reactance. The impedance must comprise a pure resistance, both at the input and at the output. Now, the input might be a microphone, or it might be the output of an audio amplifier. It might be a transducer, like an ultrasonic transducer. It might even be a loop antenna if you intend to listen to baseband audio electromagnetic signals. But in any case, you mustn't have any reactance in the input if you want the following discussion to be valid. The same is true of the output. The output might be a speaker, a headphone. It might be, a device of some kind, like a computer even in some cases. It might be a sensitive preamplifier for your electromagnetic baseband reception experiments, which I hope to do someday up in the Bighorn Mountains of Wyoming or someplace far, far away from all of the electromagnetic noise that power lines generate. Maybe if I ever do that, I certainly will create a series of videos about it, as well as probably writing a book about the whole thing. But I'm getting old and my health is starting to get questionable for dealing with the winters in the Bighorn Mountains. Well, that's a little bit of an aside. Here's the generic diagram of the transmitter. The primary winding is where the input goes. The secondary winding is where you take the output from. In this example, P represents the number of turns in the primary, and S represents the number of turns in the secondary. So suppose that you have an input impedance. Let's just call that Z-in. That's your input impedance. That's the device, the microphone, whatever. Z, the standard abbreviation for impedance. And then here, of course, we have Z out, the output impedance. Suppose that these are both pure resistances now. Remember, they need to be pure resistances. That means the devices can't exhibit any reactance. The speaker, the loop antenna, the amplifier inputs, the microphone, the headphones, whatever you use must have no reactance. If you have a particular input impedance and a particular output impedance, then they exist in a ratio, Z-in to Z-out. Or if you prefer, Z-in colon Z-out means exactly the same thing. That is the input to output impedance ratio. Now suppose that you have a particular impedance ratio. Then you need to have a different number of turns in the primary as you do in the secondary. And generally speaking, the impedance transfer ratio of a transformer with no reactance like this is the square of the turns ratio. That is to say, if you take P to S, the primary to secondary turns ratio, and you want to figure out the ratio of the input impedance to the output impedance that you're going to get. Let's move these symbols down just a little bit so there's a little bit more room. You need to square that turns ratio like that. When you do that, the ratio of the primary to secondary number of turns squared gives you your impedance transfer ratio. Contrariwise, if you take the impedance transfer ratio that you want or that you need, say Z sub in to Z sub out or Z dash out, and you want to compare it to the turns ratio, then what you need to do is take the square root. I'll make a little square root sign. I'll make it red. Well, okay, you can laugh at my bloopers all you want. This is the absent-minded professor, real-time homegrown videos here for you. Let's just call it the 1/2 power instead. That's the same thing as the square root. That gives you your primary to secondary turns ratio. Now let's work out a real-life example here. Suppose that we have an input impedance of, let's just suppose that we have a microphone here that exhibits an input impedance, very low input impedance. Let's say 10 ohms. Okay? Pure resistance, and let's say that we want to feed a really, really high impedance preamplifier with the output of that microphone. And that output is, let's just say the impedance of this thing is 100,000 ohms. We have a field effect transistor, a metal oxide semiconductor field effect transistor, 100,000 ohms. Then the ratio here, 10 to 100,000 is 1 to 10,000. We take this impedance ratio, 1 to 10,000, and take the square root of it. That's 1 to 100. So the primary to secondary turns ratio that we want here, P over S was 1 to 100. So we might have 100 turns here and 10,000 turns here, or 1,000 turns here. Well, you're going to have a 100,000 turn coil? I don't think so. 10 turns here, 1,000 turns here, maybe. Something like that. And you need to design that transformer so that the impedances or the impedances or reactances of these coils at the frequencies that you want are in the same ballpark as these impedances. So you can choose the number of turns based on that, and that is an engineering problem or an engineering conundrum which largely has to be figured out by trial and error. But that is the basic formula that we can use if you want a certain impedance transfer ratio. Now, contrary-wise, if you were going the other way, say you wanted a 100 to 1 input to output, say 100 ohms here and 1 ohm here, or 1,000 ohms here and 10 ohms here, or say 800 ohms here. Typical output of a audio frequency amplifier and 8 ohms here. Typical speaker impedance. That's 100 to 1. You take 100 to 1 impedance transfer ratio, the square root of that. It's a 10 to 1 primary to secondary turns ratio. So you might have 1,000 turns here and 100 turns here, or 500 turns here, and you figure it out, 50 turns here, something like that. And again, you would need to figure out the reactances of these coils, taking that core into account, and have it be in the same reactance ballpark as these impedances are. So you'd want about 8 ohms of inductive reactance, 800 ohms of somewhere in that ballpark. They design transformers still specifically for these purposes. So that is the basic theory behind an audio frequency impedance matching transformer, or an AF transformer. You'd think I'd learn how to spell after 6 decades staggering around on this planet, but no. Stan Gibilisco from the Black Hills of Dakota Territory, United States of America, signing off once again. Until next time, have a good night.